Dr. West is a theoretical physicist and complexity scientist who has made significant contributions to our understanding of complex systems in both physics and biology. His research focuses on developing quantitative models for understanding the behavior of complex systems, such as cities, organisms. His most famous works in the book is the book, quote, Scale, the Universal Laws of Growth, Innovation, Sustainability, and the Pace of Life in Organisms, Cities, Economies, and Companies. Woo, that's a long book title. So
it's a long book.
Oh, how many pages is it?
Well, it is actually over 400. It's about 450. It was supposed to be about 250, but once I started, once I got over the initial hump, it was hard to stop. Lots of things to tell people about.
That's absolutely correct. So, this is the most important thing I care about. What are you working on right now? What's got your interest? What do you love?
Well, working on many things that actually span that spectrum in the title of the book. But I would say my kind of passion in the immediate future and what I've been doing recently is focusing on the whole question of global sustainability, in the sense that, can we really understand what the dynamic of the planet as a whole is? And is it in fact even conceivable that the kind of remarkable socioeconomic system that we've sort of evolved on the planet over the last 10,000 years, which is a big question. So it involves all kinds of questions about what we call phase transitions, meaning tipping points and singularities and so on and so forth, and the whole question of exponential growth and blah, blah, blah.
Right. I kind of followed a good bit of it at Google and your TED Talk and stuff, but I'm loving that you're going into this. Please feel free. Continue.
Well, when you heard those talks were sort of just the beginnings of this kind of thinking in terms of the planet. And it's only in the last 6 months or so that I returned to that, mostly because a whole bunch of new data appeared, and which allowed me to sort of make more progress. And because being a physicist, unless there's data to really test your theories, make predictions, test your theories, I don't feel comfortable. So I put it all on the back burner, even though I talked about it, 5-10 years ago, even the last couple of years, but it wasn't central. Now it's become central, even though I work on many other things, by the way, which maybe we'll get into.
Oh, we will.
But that is the one thing that I'm feeling sort of a certain urgency.
If we can't find the evidence, what are we doing? Right.
Yeah. So I'm quite, and I get very frustrated with that, because on the one hand, of course, we want, people to speculate and think and sort of use their intuition and bullshit in the positive sense of that word, and have, obviously, to keep it, kind of qualitative discussion and thinking. But, as I say, coming out of physics, I feel until we make it quantitative, we confront it with data and observation, possibly even do an experiment or two, and really test the ideas, it remains a little bit, an inverted pyramid. It may collapse any moment. So I'm very, I take a kind of hard-nosed, maybe more than most, hard-nosed kind of attitude towards feeling uncomfortable until I have, data, or potentially have data. I mean, I don't, have to write it to fingertips.
Right. Really, we can have well-informed and academic hypotheses, right?
Sure, absolutely. And we need to encourage more and more of those. Mm-hmm. But, ultimately, you want sort of quantitative, analytic, computable, predictive kinds of theories or models and so on. And I think that's where doesn't have to be all that, but science progresses best when we do
Yes.
that.
Yes. I feel as though I lean towards methodological naturalism, and until we find evidence for things that aren't within our parameters, we shouldn't just throw our beliefs to the wind and to every whim and fancy that we have, right?
Yep.
Yeah. So let's, I really want, I studied about complex systems for this talk, but I really, especially the emergent properties or the epiphenomenalism of it, tell me in your way how you see complex systems. It doesn't matter if you want to get started with ecosystems or however you want to explain it.
Well, yeah.
I gave you a big question, didn't I?
That's a big topic, and it's one.
Oh man.
I mean, it's so. The focus or the recognition of complex systems, and in particular, what we've come to term complex adaptive systems, mean, recognizing that the most interesting systems and the ones that are most challenging are those that are evolving and adapting to changing circumstances. This has only been an area of serious study in the last 20, 30 years, really. And it all sort of started to come together with the founding of the Santa Fe Institute. And that's been sort of the central hub of this globally.
You've been there for a while, haven't you?
And I've
2003?
been there since, I've been there officially since about, I think, 2003, 4, but I was interacting quite strongly in my early work on this since the mid-90s.
Right.
But it's been, defining, if you like, complexity and complex systems, and what are the boundaries and characteristics of a science of complexity is an ongoing debate, and it will remain so because of the very nature of what it is. And many of us are kind of familiar with what a complex systems is. It's that famous quote of who was it? The judge that made the statement, when they were discussing pornography in the 60s. And God, I'll get his name in a minute. But
we were talking about this the other day. It's on my tongue. Sorry.
Yeah, he made this famous statement, I can't define pornography, and I can't really explain exactly what it is, but I know it when I see it. And I think that's how many of us feel about complex systems. But let me just say a few words, having said
Please.
all that. So we recognize it in the sense that, thinking about the economy, or thinking about the weather even, thinking about how does a city work, how does a company work, how does your body work, what is consciousness, all these wonderful big questions. We all recognize that they're not like the kinds of questions that I was involved in much of my career, which is physical systems, like the solar system. The solar system, I can write down as a physicist in 2 lines, the 2 equations that basically control the dynamics of the solar system and allows us to predict where the planets are, the motion of the planets.
Is that the Dirac equation and something else?
No, that's just simply Newton's laws. Newton's
laws. Yeah.
F equals ma, and Newton's laws of gravitation, that the force is proportional to the mass. It goes inversely as the square of the distance. Basically that tells you everything. I mean, it's extraordinary. But it not only tells you about the motion of the planets, it tells you about, so to speak, all motion, really. So anyway, the laws of physics, quantum mechanics, electrodynamics, relativity, and so forth, are very precise. They give precise predictions in the overwhelming majority of cases, and they can be checked to almost arbitrary accuracy. And that's sort of been an enormous success, and in a certain sense has underlined the progress of sort of modern science and modern technology in various forms and to varying degrees. But and that is sort of the ultimate success of modern science, and other sciences of course, have may want to aspire to it, but the sciences of biology, that is, how organisms work,
Mm-hmm.
and the sciences of psychology or psychiatry, how the brain works, or neurology, neurobiology, and then the sciences of economics and so on,
Right.
struggle because they can't be reduced simply to a bunch of simple equations, typically. And part of the reason,
Especially the economy. Especially
especially the
the
economy,
economy.
as we
Do
as
you
we
think
know.
there's more math? Do you think there's more math in economics than there is in theoretical physics?
Well, that's one of the great ironies. There may well be, and
Yeah.
yet, the success, the ratio of success to number of equations
Mm.
is is completely inverted.
So you could be, in computer science, like systems analysis, obviously, right? You've dealt with that before. Could you say that on these complex systems, like a network or a ecological system, or could you say you're just doing a systems analysis of that? Is that a oversimplification, or?
Oh, well, it depends really a little bit what you mean by systems analysis, but the important point here is that complex systems has the word system in it,
Yeah.
which means that it focuses on the system as a whole and the seeing things a little more holistically, a little more in a more integrated way, and most importantly, that it recognizes that all parts of the system are interconnected, even if in some cases they're weakly interconnected. And indeed, the pandemic, which I was going to just say we went through, but in fact we're going through, and we're still in
We
the
are.
middle of the bloody
Yeah.
thing, actually.
Hmm.
Uh, but the pandemic is a fantastic manifestation of the sort of conceptual framework of complexity science and complex adaptive systems, because who would have believed that a sort of random mutation of a virus in Wuhan, China, would lead within a few months to no football in Spain, shortage of flour in the United
Hmm.
Kingdom, Hertz going bankrupt,
Hmm.
all of these things happening within just a very short period of time, and all seemingly disconnected, and
But
yet
not.
but that's the point. Actually, before the pandemic, they were connected, even though very weakly. I mean, believe it or not, the production of flour in the United Kingdom is actually very weakly connected to the having football in Spain,
That's
or
true. Yeah.
or the health of Hertz Rental Cars, a company. They're always weakly connected. They're weakly connected now. But the pandemic, the beginning of that virus mutation, enhanced exponentially their interconnection. And so suddenly we saw that the whole planet was interconnected. And it's a bit like what we call a phase transition, or
Mm.
when water freezes to ice.
Yes.
I mean, in the sense that, when you look at, in a cup of water, the molecules are, mostly, almost overwhelmingly, each molecule is only interacting with the local ones, with ones very close to it.
Yes.
Of course, because it's interacting very strongly with ones close to it, there is a very weak connection to the ones a long way
Further
away.
away. Yeah.
But it's small, and it doesn't usually matter. But as you lower the temperature and their energy gets lower and lower, suddenly there's something which we call long range order.
Mm.
Suddenly, the connection of that molecule with the next one stays strong, but the ones connected to farther away get stronger and stronger, and suddenly everybody's acting coherently, and
Mm.
the whole thing freezes. It's all one thing, and water, instead of flowing, suddenly becomes rigid and turns
Yeah.
into ice. But all those molecules are suddenly interconnected in a kind of lattice. So that is sort of, I mean, it's a loose metaphor of the kind of phenomenon that occurred has occurred and is occurring in the pandemic, where we see the close interconnection between all things. And this is a typical characteristic of complex systems. And, that's interrelated to the fact that a complex system typically contains enormous number of agents, enormous number of, a city, a large number of people, an economy is obviously a huge number of components, and so on and so forth. And that is the big challenge, and they're all interacting with each other, and they all have very different scales in which they interact, so that we have these kind of emergent phenomena that occur.
Yeah, from the complexity of the system, right?
Of the system.
Yeah.
New things emerge that were not apparent in the individual. I mean, buried inside you, you are not a city. In fact, you can't exist on your own, of course. No human being can exist on their own. There isn't such a thing as an individual human being in the absolute sense. We are all interconnected with each other. And, part of the emergent phenomenon of our interaction is a city.
Yes.
And which is much more than the sum of all our individual interactions. A city is not the sum of all its people or the sum of all its roads.
Yeah,
or
it's more. Yeah.
So much more than that. And it's a new thing of itself.
Yeah. So strong emergence, right?
Strong, very strong emergence.
Strong emergence. I'm with you on that. I think that many things we can look at in terms of strong emergence. I had something on my mind I was going to ask you, and then I forgot it. It doesn't matter. Let's see if I got a really good friend here. His name is Tart, and he is a brilliant person, and I'm going to see if he's got anything to say. Tart, what's up?
Hi. I'm mostly just thinking about the implications with this and things like philosophy of mind is where I was thinking. So like the idea that the mental, like our conscious things come from things that are themselves far more simplistic, but that complexity ends up making into our sort of conscious states. I don't have any major questions that are coming to mind just yet, but I will definitely let you know if something comes up.
That's
Well,
okay, Tart. I just wanted to hear your
let me just pick up on what he said, what Todd said. The brain's another phenomenal example, of course, of an emergent phenomenon. It's made up of neurons, but each neuron and each bunch of neuron actually doesn't have any idea that it's part of this brain. It's the whole thing. It's the whole thing interacting, and that emergent phenomenon is you. Even though, but you don't know, and you are not conscious of your neurons.
No, we aren't.
Of the individual that are making you, and that is quite mystifying. That whole phenomenon, and the challenge of science is how do you put that into a logical, kind of rational, predictable, understandable structure.
Yeah, neuroscience formally is attempting to put it into some kind of computational system to where it's like epiphenomenal, the workings of the brain cause that strong emergence. If consciousness exists in the way that we think it does, I think it is just a fact that the brain is so complex that it emerges consciousness. I don't know, because I'm very into philosophy, so consciousness is a big topic, philosophy of mind, all that stuff. But I'm more interested here in, of course, the science. You know what I mean? I'm a physicalist. I'm a scientist. I love that stuff first and foremost. And I loved your quote about evidence earlier. I thought that was great. Hume actually said the wise man apportions his beliefs to the evidence. So, let's see what, I really want to, are you working on a book right now?
No, when I finished my book, I said I will never write another one again. It was, it majorly cost me, but I enjoyed it immensely, and so on. And I felt, I know this sounds a strange thing to say, I really had nothing more to say, really, which is a weird thing to say. Of course, there's lots to elaborate on, but in the intervening time, especially recently, I have started to rethink that maybe it might be time to rewrite. And part of that comes out of two things, actually. One thing, what I tried to do in that book was I did not want to pull things out of the hat. every time something came up, I felt I would want to explain it to the quote intelligent layperson.
Mm.
So I even spent, if anyone's read the book, they will recognize it, three or four pages explaining what an exponential is, because in my various peregrinations and giving talks to corporations and at major events, I discovered that many very intelligent people, many people with a lot of power making decisions, use the word exponential, but don't actually understand what it is. So I spent time telling people what exponential. So that was an example. Now, that made the book much longer, actually, and that's one reason it was, because I gave very simple and I hope amusing examples of what some of these terms meant. But what I realized is, in writing another book, I'm now liberated from having to do that because I've done it. That is, I don't have to explain. I can say to people, look, just go read my book. I'll even give you a reference. Read those pages if you really want to understand what this term means, whatever it is. So that's liberated me a little bit. And the second thing is arrogance. Because in the meantime, many books have come out related to the kinds of things I was talking about. My book, as you articulated the title, covers an enormous breadth and enormous territory. And books have come out on specific things. And I look at these books, and some of them have been bestsellers, and I think, shit, if they'd only read, all they need to do is read chapter 8 in my book, and they would have covered everything that's in this other book in a much more elegant way. That's my arrogance.
That's okay.
That led me to think, well, maybe I should I should write again about some of these things and expand a little bit. And certain things I did not talk about, I took out of the book. Which were, I felt were important, but a little bit tangential. For example, I didn't talk a lot about sleep and the brain, which is something we just touched on a teeny bit. But, about what is sleep, how does sleep work, and how is it related to the structure of the brain, and some ideas about consciousness and so on. So there are all
neurogenesis, yeah.
But in particular, the two things that I would do if I wrote another book is expand on the last chapter or two when I did start to get into sustainability questions, the future of the planet, the resilience of our socioeconomic system.
That's mainly what I want to know about. That's mainly what I want.
Yeah. And its fragility. And the other thing, which is actually related to it, and that is the whole idea of time and the acceleration of time. That is, the time that we really live by, our socioeconomic time, has been speeding up inextricably. And I talk about that a little bit in the book. And that is in contrast to something that fools us, which is the time that's on our clocks, which is very linear and has got nothing to do with socioeconomics. It's to do with the planet spinning on its axis and moving around the sun.
That's right.
And it fools us, that time. But so to speak, the real experiential time is driven by our social interactions and our neurobiology and so on.
Yeah.
And I want to explore that. And what I want to explore is a consequence of the speeding up of time, and that is that it's getting harder and harder for us to adapt to that acceleration.
Yes.
And we are our brain, which we just talked about briefly. Our brain and consciousness and our biology are the same as it was 10,000 years ago when we started on this journey, when we learned language, and built communities, and then cities, and then this fantastic existence that we have now. But we're the same.
We are.
But our externalities are completely changed. And we have adapted. I mean, one of the mysteries to me is how extraordinarily well we've adapted to the changes we have invoked and stimulated.
Yeah.
And the question is, what's the limit to that? Is there a limit to how quickly we can? I mean,
I've thought
I've
about
had
that
to
many times. Like, is the internet, all the technology super quick in the last
right.
100 years. The complexity
It's
of that system alone altogether, wow.
absolutely.
Yeah.
And so, look, I'm 82 years old, and I still go on doing my research, and I collaborate with most of my collaborators are less than half my age, and I have to adapt to, suddenly they say, "Oh, this thing is in overleaf." I say, "Overleaf? What's that?" So I have to learn overleaf. Well, then we go on and they say, "Oh, now I put the document in Google Docs." Google Docs. Well, and so on and so forth. And then, well, we should really conduct this on Slack. And this is happening, every few months there's another bloody thing for this poor 82-year-old brain.
And then now we got this one that's just barely holding itself together. We're still working on it.
So there's all that.
Just keep on
I had to get
proliferating.
I had to get my iPhone 14 because my iPhone 6 no longer was, So it's happening faster and faster. And, so I'm very conscious of it.
What's the height? When can it stop? Does it stop?
And can it stop? Or is it leading us over the edge of a cliff? So, this is just one piece of the whole thing. We got the whole globe. And so this is what I'm working on and what I would write about if I can get up the courage and still have the discipline, which is harder, actually, the discipline and energy to write another book. I don't know. I'm struggling with that at a personal level, and maybe I would do it, maybe not. But I love talking about it. Meanwhile, it's much easier to talk about.
Yeah, it is. Follow your heart. I know that sounds cheesy, but I think you'll do what is in your heart.
Yes.
Man, so I guess the most important thing is the socioeconomic impact and how we conceptualize these structures, these systems to analyze. So what can we do if we can analyze these systems? What can we change?
Well, this is, I think, I'm going to change your question slightly.
Okay.
So I and others, of course, are grappling with some of these problems. But the other issue that comes up is even if we're hugely successful, I mean, these problems are incredibly challenging, extremely difficult, and almost certainly not entirely soluble for sure. But maybe we can make some really serious progress, and we can really find a way in which, we do have to adapt and change, and we have, we can inform practitioners, politicians, leaders, and so on. But that's the problem. Does anybody listen? Is anybody actually, anybody that can really effect change listen? Because we've been through a very difficult, one of my speculations, and it's purely speculation, is that this problem of the speeding up of time and all the other things associated with it has produced great anxiety and because it's kind of curious when you think about it, the standard and quality of life has by and large, despite all of our problems and despite the increase of inequality, has actually continued to rise. So it's high. We have more fancy, sexy things now than we did 25 years ago, 50 years ago. And yet people are...
You're fine, man. You're fine.
Okay. And people are getting, and yet people are getting more and more dissatisfied, more and more anxious, more and more unhappy, and so on.
The rise of mental disorders, more so.
Exactly. All of these things are happening. Yeah. And why is that? And so it's kind of strange. And so somehow the way people have reacted to it is turning to, instead of confronting the problems themselves, turning to simplistic answers. And that's why we end up I hate to say it, um, electing a Donald Trump
Yes.
or having a Putin.
Yes.
Or having,
Yes.
you know, or back in Hungary or whatever, you know, the rise of kind of
The
these
demagogue.
authoritarian rulers
Yeah.
who do have, or Netanyahu now in Israel, you know, having very simplistic answers to extremely complex and challenging problems.
Oh, that's what the demagogue always wants you to believe, is that I have the answer.
I have
I'm
the
the one
answer.
who can fix this. You know what I mean? It's kind of disgusting, but
So that's that's a huge issue, and so even if scientists and others can come together and really find credible solutions to some of these problems, all of which are going to be difficult, challenging, and require significant change. I don't think we have the leadership to do it. I mean, it's almost like it's crying out for Martin Luther King or Jesus Christ or Muhammad or someone that has that kind of charisma and power, but projects, I hate to, love thy neighbor as thyself. You know,
I've always said it's going to take the largest grassroots movement in history with so I don't know how to do that, but
but that's the point. And usually such huge movements require, you know, a charismatic leader. And Donald Trump, you know, one of the things, I mean, he is charismatic and he obviously tuned in to, you know, something that was, that many people felt. Unfortunately, you know, he projected, you know, well, as far as I'm concerned, the wrong answer. You know, leading us into even more difficulties. And
I would
so
say
we need
that's a road
someone
of
with the charisma,
yeah.
but that has, you know, that preaches sort of the opposite. That you know, that we should be more caring, more humanistic,
Cooperation.
more love is the.
I tell
It
everybody,
sounds so
you know,
sickly.
I've studied the ethics of morals, meta ethics and ethics and all this kind of stuff. But I start with one moral axiom: love. And if I try to derive everything
Yeah.
from that, and I know that sounds cheesy, and people can make fun of me for it all they want to, but it's just a part of who I am, and I love that I love. So, so you
Yes,
see,
I respect that.
I appreciate that. I see that you feel the same way too. So you see the main problems of understanding all these complex systems as being mainly socioeconomic, because that's what's driving a lot of the faster pace in time, right?
Yes,
Okay.
yes. It's sort of built into our social networks
Yeah.
in many ways. You know, I mean, social networks have this extraordinary capacity that when we interact, especially, you know, I mean, not just one on one, but in groups, you know, A talks to B talks to C talks back to D, and we build on each other.
Yeah.
And we build, and we're continually creating ideas. That's what you know, a great discovery of language and exploitation of it has allows ideas to be continually being generated. Of course, essentially all those ideas are useless and irrelevant to everybody else. But what is extraordinary, that dynamic, that positive feedback dynamic building on each other eventually leads to, you know, the theory of relativity or quantum mechanics or a Google or an Amazon or a Toyota or whatever.
Yeah.
You know, I mean, that's what we do. And that's been our great success. And but it somehow also is connected with the need to want more.
Yeah.
And wanting more of ideas and so on is great. Wanting more love maybe is great, but just wanting more in terms of materialistic and greed, you know, maybe has been a positive driver in some respects. I don't want to dump on it,
No.
because that's been, you know, that is in a certain sense integral to our great success. You know, capitalism and free markets and entrepreneurship, people wanting to get more has been a driver. On the other hand, it has also been fraught with the kinds of evils that have, you know, encompassed the world.
Oh, yeah.
And so, you know, we haven't been, as a species in terms of this new phenomenon, new meaning in the last several thousand years, we haven't come to terms with, actually.
And then in 1995, we have the internet dropped on us.
Absolutely. Which, at the time, in the 90s and in the early 2000s, it looked like, my God, this is going to be something that's going to bring us to, I don't know what, but something. What did bring us to something extraordinary.
Yeah.
But again, the unintended consequences problem of complex systems, built into complex systems, things that you didn't realize were interconnected. Who would have thought the innocence of Facebook? So for all the shit that Zuckerberg gets, maybe rightly so, the original idea, of course, of Facebook is a wonderful idea. I mean, by the way, I've never used Facebook. I'm not a subscriber, but I mean, it apparently was extremely positive in the beginning, bringing people together, being able to share, and so on. Who would believe that social media would end up, really dividing the world, dividing people.
Because all these other countries use Facebook to get their news. You know what I mean? And it gets wild like that.
So this is, so again, we haven't really, and the other issue, again, speed, this pace of life entered into it because it happened so quickly.
Yeah.
We the system, so to speak, meaning us, hasn't had time to absorb it and adjust and adapt in a way to really exaggerate the positive rather than be brought down by the negative.
Yeah, we're counting the misses and ignoring the hits, right?
Yep.
When we
so this is what's happened. So I think so it's all very highly interconnected. This problem, the accelerating pace, and these marvelous technologies that the positive feedback and creation of ideas in social networks produce. It's and I'm not at all sure how we're going to come to terms with that. So I've sort of more and more, despite the fact that I'm a sort of fundamentally optimistic person, I'm getting more and more pessimistic about the long-term future. And this, because the work that I've been involved in terms of looking at the growth of the socioeconomic system leads us, I mean, the data is telling us that we're leading towards what we call a singularity.
Yes, technological singularity.
The analog of water freezing to ice, meaning something, it's the same constituents, but they're now, in a completely different state than they were before. Like water and ice are the same stuff, but they are completely different physically. And, that's a bit scary if we think of us, I mean, we're, most of us, we do pretty well in the present system. I love it. I love what we've created, despite all of its issues. But, we may be heading towards a singularity, therefore a transition that is going to lead us to collapse.
I hope it goes on forever, but I see exactly where you're coming from. You know what I mean? I think there can be some kind of a pessimism there because I do see what you. Go ahead.
No. It's we need to be cognizant of that. We need to be cognizant that
we always think it's like this upward. We always think it's like this upward curve of humanity that's just like getting better and getting better and getting better. But we're not, like you said, we're not keeping up with that socioeconomic pace of time.
No, and we have this what I consider naivete, that we can always innovate ourselves out of it.
Yeah.
And, that another innovation will come along that would change things so that we're fine. We had the computers and then we had the internet. Goodness knows what there has to be another one.
There has to be.
It might just be electric cars. It might be self-driving cars. It may be AI and machine learning.
Yeah.
But these will have major impact, no question. Certainly, AI and machine learning already. I mean, AI has been around actually for 50 years.
Yes.
But so it's not new, but its recognition and its power have only been realized as we all million in the last couple of
Yeah,
years.
they had the AI winter for a while there where it was just
Of course.
non-existent, and then it
Yeah,
pops up
exactly.
huge again once we understand the ramifications of the internet and like phones and
Sure.
all this kind of stuff. I kind of well, I don't want to real quick. How long do we have you for, my friend?
Well, I'm fine certainly for another half hour.
Okay. Well, let's because
It's up
I'm
to you.
hold Oh, so go ahead.
No, I'm fine. Let's see, it's 11:40 here for me, right, basically.
Okay.
Yes, I can go on for at least another half hour.
Okay. Well, we've got I want to talk to you for
But also, by the way,
yeah.
you're welcome to end it at any stage.
No. I want to go on as long as you want to talk. I'm enjoying the hell out of this myself. I love talking to you, but we've got a couple of people in the caller queue, and I don't want to ignore them. So let's
Sure,
go on to Ryan here, and then we'll go around my stage and see if we've got any good questions for you.
sure.
Okay, Ryan, you're up. What's up, man? We got
Hey, thanks
anything
for
on?
being with us, Doctor.
Yeah.
And just wanted to say that, the cool thing about being a pessimist is you're only pleasantly surprised, which is a good thing. You're always ready for anything. So I appreciate
Right.
pessimists actually quite a bit. And my question is about gravity and like gravity waves and how do they relate to, maybe you can help me understand them better. The way I understand the quantum field is it's like a combination of like gravity, electromagnetic waves, or electric and magnetic waves, and all together, and that it's different phases of the quantum field that determine whether or not it's acting as gravity or magnetism or whatnot at a certain time. I'm just now starting to understand all that, try to wrap my head around all this, but I'm
Yes.
curious about gravity waves. Are they anything like electromagnetic waves?
Yes, they are in many ways like electromagnetic waves, but they don't have much to do with quantum mechanics directly. They one of the things that just go way back, to electromagnetism. So in the 19th century, James Clerk Maxwell unified electricity and magnetism, which were considered, people had seen as two completely separate things, but there was enough evidence that there was interconnection between them. That if you move something that is electric, it can create magnetism. So they were clearly interconnected, and Maxwell found the fundamental equations that made them totally interconnected, so that there is just one thing, not electricity, not magnetism, but electromagnetism. And they're called Maxwell's equations. And one of the things he quickly realized, which was quite extraordinary, was that these equations implied electromagnetic waves. So he made this extraordinary prediction of electromagnetic waves, which may be the most profound prediction out of science in terms of its impact on human beings that is ever made, because we wouldn't be able to do any of this without electromagnetic waves. none of all the simple things like just radio and transmitting messages to all the way to the internet now. The motion of things with gravity, which was in a primitive form in Newton's laws going way back to the 17th century. But Einstein really bound it up with the whole structure of space and time, and that's where the idea of relativity came from. But as I say, one of the consequences of that was that there would be these electromagnetic waves, meaning that just as when you move electrons, you move you move, so to speak, things that have electrical properties, they produce electromagnetic waves. So it was that he realized that actually what his equations were implying was that if you move something that has mass, that is sensitive to gravity, you might produce gravitational waves. And he actually didn't like the idea too much.
So gravitational wave, real quick, gravitational waves is a classical concept, right? Within relativity.
Yes,
it's
exactly.
Not, we don't have any evidence of gravitational waves.
You don't have to have quantum mechanics to get gravitational waves. Okay. So just as if you move, the fundamental sort of particle of electricity is the electron. And if you move an electron, if it just moves, not just straight, but if you accelerate an electron is maybe what I should have said. If you accelerate an electron, it produces electromagnetic waves. And all electromagnetic waves that are around you are produced that way. That's exactly how they're produced. So the analog to that is if you move a mass, it produces a gravitational wave. Now, the difference between them is that the strength, so to speak, associated with gravity is, is it 40 orders of magnitude? No, 38 orders of magnitude. That's 1 with 38 zeros.
A lot.
Weaker than electromagnetism. So the chances that you'd ever see it were minuscule. On the other hand, of course, if you had an enormous mass, which of course is out there in the cosmos, maybe those things moving might produce gravitational waves that you could detect. And that has been on people's mind for the last 50, 60 years. Could we do that? And for many years, people tried and it was sort of felt impossible and so forth. But then, of course, as our technology improved and our sensitivity, our exquisite sensitivity to small changes was developed, people realized that you could have an experiment that potentially could detect gravitational waves that were produced out there in the cosmos. And so this famous experiment, LIGO, the Long Range Interferometry Gravitational Observatory, I believe it stands for. LIGO was invented. So the idea being that since we now believe in black holes, that the collapse of a black hole or some change in the black hole would produce gravitational waves and we would detect them. And that was one of that indeed, as you well know, happened and was an extraordinary accomplishment. And by the way, an extraordinary technological accomplishment, let alone accomplishment of pure science in predicting it. And so gravitational waves, on the one hand, I mean, the equations are quite extremely complicated and so on. But the idea is simple because by analogy with electromagnetic waves, namely the motion, just to repeat what I said, the acceleration of an electron. Yeah. So if an electron changes its course, it sends out an electromagnetic wave. So if there's any acceleration of a physical mass, that sends out an electromagnetic wave.
Okay.
So the universe is full of gravitational waves, but they're so weak, we barely feel them.
Yeah. Wasn't real quick, Brady, real quick. They discovered it using lasers, right? Where they had this like long, like L-shaped.
Well, they do.
Yeah.
Exactly. They do interferometry.
Yes,
so
yes.
One of so that,
how minuscule was it? Was it, you said the order of magnitude? Is that what you were talking about?
Oh my God. I don't know the numbers any longer.
Oh, that's okay.
I'm afraid.
That's okay.
But it's equivalent to, or I think it's equivalent to the being able to detect the motion of a proton inside a hydrogen atom. I mean, it is absolutely astonishing.
Wow.
The use of technology to detect such tiny changes. And that's been the power of physics.
Yeah.
And just to go back to the beginning of our conversation, you cannot conceive of anything like that, probably even in principle, for complex systems. That is, we're never going to be able to predict the future of the economy, or the dynamics of a city, or the weather, to anything like that accuracy. I mean, but nevertheless, we should try to develop a science that develops a kind of much lower resolution or kind of coarse-grained kind of prediction for the future of the weather, the economy, or what I'm trying to do, the future of the planet.
Well, like you said, it's never going to be exact in those. It's not going to be like the Planck's constant or something like that. It's not. It's so dynamic. I mean, it's like, if I may, it's like butterfly effects on top of butterfly effects, is what
Absolutely.
It seems like.
But it shouldn't stop us trying to develop a theory for complex systems and for the future, in particular, the future of the planet, and so on.
Yeah. Let me, real quick, Brady, I appreciate your question, brother, but we're going to go to GHC next. Brady, if we're on for a little bit longer, I'll get you back in here, okay? Thank you for your questions, bud. All right, we got GHC. It's one of my buddies from our Discord. What's up, man?
Hi. First of all, thank you very much for your talk.
Yeah.
To both of you.
Thank you.
I was wondering if we could just elaborate a bit more on exactly what you just finished on this idea.
Oh, gravitational waves?
No. Rather the idea of how to develop a science of complexity. So if
Oh boy.
if I just say a little bit about it, there's obviously the night bottom of not causality but correlation. Yeah, and if you think that the solution is closer to decompose the system and into its subparts, or the other way around, so wrapping it around and trying to rather instead of trying to predict the atomic parts. Yeah, thank you.
Yeah, sure. Yeah, this goes to the, of course, I could spend
eons
the rest of the afternoon talking about this, but first to this last point or question that you raised, there is this tension between reductionism and thinking in a more holistic, integrated way. So traditionally, science, and especially physics, but most of science, all science is reductionistic. We try to reduce things to their elementary components, and then the idea being that the whole is built up from the dynamics of those individual constituents. So, beginning, way back with the ideas of that, everything is composed of atoms, and what we see is actually the composition, the collective behavior of all of these atoms together. And so reductionism, going down, and I'll stay with physics for the moment, beginning with atoms and then realizing that there are, that there's a nucleus and there's electrons going around it, and then inside the nucleus there's protons and neutrons, and inside protons and neutrons there's quarks and gluons, and then maybe inside those there's strings and so on. So there's this kind of hierarchy and level structure, and that paradigm has been enormously successful. I mean, that science has progressed enormously by reducing things to its component parts and trying to understand the dynamics of those component parts, and then even trying to reverse that process by building back up. And and in biology has sort of followed that, of course. We go down to, we realize that organisms are made of cells, and inside cells are things called organelles, different components of the cell, and inside those are kind of genes and respiratory complexes and so on. And the idea, if we study those in great detail, we'll understand the organism. And I think what happened beginning in the 80s and 90s was the realization that, yes, it's wonderful to dig deep, and we've revealed some wonderful things, and we've learned many things, and it's been in many ways very successful. But in terms of understanding the whole, in understanding the system, in understanding your brain, understanding your body, understanding a city, understanding an economy, understanding a company, it's been woefully poor because we've, the well-known statement, almost a platitude, the whole is much more than the sum of its parts. And I've already said that earlier. A city is not the sum of its people. A company is not just the sum of all the workers, and so on and so forth. It's much more than that. And there is this idea of emergent phenomena. And it is from thinking along those lines that the whole idea that we need to develop, or at least we need to be thinking about, a science of complexity that develop of itself. And so I got into it because I became fascinated by things called scaling laws. Because one of the things that I learned, even though I was doing physics, was that there were these extraordinary scaling laws in biology. Namely that, for example, if you look at the most fundamental quantity of life, which is metabolic rate, that is how much energy, how much food does an organism need per day to stay alive? Because that's obviously fundamental. It's fundamental to your life, but it's fundamental across all life. Right. It's called metabolic rate, and you're no doubt very familiar with it. You ask how much, that's the kind of 2,000 food calories a day for us. How does that change as I look across all animals? Well, this was answered 70, 80 years ago by a man named Max Kleiber. And he discovered something extraordinary, that if you plot it logarithmically, now what does that mean? That means if you plot it, instead of going up 1, 2, 3, 4, you go up by factors of 10, 1, 10, 100, 1,000, 10,000, and so forth, 100,000, a million. If you do it that way, and he did it that way because he was looking across all organisms, and he was going from mice to elephants to whales, and that's a factor of 100 million, and you can't do that on a linear plot. You'd have to have a piece of graph paper, I don't know, I'm probably exaggerating, but the size of Chicago. So in order to compress it, you plot it in this so-called logarithmic way. And when he did that, he found the metabolic rate lay on a straight line. It was extraordinary because metabolism is probably the most complex process maybe in the universe. Namely, you take stuff and you turn it into life. I mean, that's basically what metabolism means. That is pretty amazing. And so here it is, and it's fundamental to all life. And you plot it, and you get a straight line. So here's this most complex thing. Not only that, we believe in, at least I hope we all believe, in evolution and natural selection.
I do.
Namely that each organism, each one of these organisms, each subsystem, each organ, each cell type, each genome has its own unique history. Everything is historically contingent. It depends on all kinds of frozen accidents in the past, all kinds of environmental niches that are continually changing, and we're continually adapting and evolving. So you would have expected, had you made this plot of something like metabolism, which is fundamental to life, that the points would lie sort of scattered all over the graph, sort of reflecting this historical contingency. Not the case. So I got very intrigued by that. Not only that, the slope of this line had this weird number 3/4, 0.75. So that was fascinating. But what is also fascinating is if you look at any physiological quantity, meaning something as mundane as the length of your aorta, or it could be, the diffusion of oxygen across some membrane, or any life history event, like how long do you live? How long do you take to mature? How many offspring do you have? You plot any of those in a similar way, guess what? They're straight lines on this log plot. Not only that, the slope of these lines, just like metabolic rate, are simple multiples of 1/4. So
that's interesting.
So, for example, I'll give you another one, heart rates. If you plot heart rate versus size of mammals, there's a nice straight line, which is decreasing rather than increasing.
Mm-hmm.
Slow heart rates get slower the bigger you are. And the slope of that line is minus meaning it's going down 1/4. So this was true of all of them. And I could spend the afternoon telling you 50 of these things. So I got very intrigued by that. And to cut a very long story short, I worked with some biologists and found the underlying principles and the mathematics and physics that derive from first principles the origin of this 1/4. The magic number, the spiritual number of the biosphere around you is 4. That's it. 1/4. And the origin of it was the thing that is common across all organisms, and that is it has to distribute energy and resources and information throughout the entire organism. And this is true of all complex systems. Mm-hmm. And so, and how does it do it? It does it by networks. We are, when you think about it, you are just a bunch of networks.
Yeah.
You are a bunch of networks.
We are, yeah. Mereologically, we are just a combination of networks.
Your circulatory system, mm-hmm. your respiratory system, your renal system, even your bones, your neural system, your very your brain is a network. And it is the mathematics and physics of these networks that gives rise to this quarter power, this four. Mm. And one of the things that's built into that derivation is a huge assumption, and that is that natural selection, the continuous feedback, the continuous honing of the system because of competition, has led to these networks being in some sense optimal. So, for example, your circulatory system, the system that supplies resources, oxygen and resources to your cells, carrying it through blood in your circulatory system, the one that we have, and by we I mean not just you and me, all human beings, but all mammals that have ever existed, the ones that we have minimize the amount of energy that your heart has to do to pump blood through the system to supply cells in order to maximize the amount of energy that is left over to have sex and reproduce and raise offspring.
Right.
So that's the idea. It's called to maximize Darwinian fitness. Mm-hmm. And if you take all of those words that I said and put them into mathematics, amazingly, out pops all these scaling laws. And not only that, it tells you the structure.
That's crazy that it's a straight line at like quarter intervals.
Feynman and so on, but unify it with the weak force, which is the force that is actually allows the sun to shine, the weak force and the strong force. The strong force is the nuclear force, but unify all of those with gravity. And so we have one marvelous unifying theory, and we sort of understand it at its most fundamental. That would be just a phenomenal achievement, and I think it would be very beautiful. So that's one answer. But I have something at the complete other end of the spectrum. There's something I'm sort of scratching the surface of, which is a grand unified theory of global sustainability. That is, we bring together the dynamics of the biosphere with the dynamics of the anthroposphere and understand this interrelationship between where we came from, that is biology, and our interface and interaction with the rest of nature, meaning the biosphere, which produced us, but understand this divergence that has taken place where we form this socioeconomic life, which I refer to as the anthroposphere, and see how that works, really understand that in a dynamical, quantitative, predictive fashion, so that we can, with credibility and with some feeling of confidence, craft our own future and really maintain what we have and not collapse and return to being hunter-gatherers.
Yes.
So, that's nothing wrong with hunter-gatherers, but I really love this. I love being able to talk to you, this distance, and better see you and better hear these voices and so on. So, this is something extraordinary. We are, and by the way, part of that is, you talked about love as fundamental. Well, I agreed with you, but I have something coupled with that, and that is I see the meaning of life, so to speak, as being love and understanding. We are here, we have somehow evolved so that the universe can understand itself. Otherwise, the universe is meaningless without us or some consciousness. And I don't like that. So I'd hate for that to go. That would be.
I would hate for it to go too. I mean,
what a tragedy.
I think we need a comprehensive rewrite, just like you said, of systems science. I think we need a full field devoted to it and lots of funding. Do you have time for one more question? Because I have
I'll take one
more question. Okay, our friend Don had one. He texted me, and it's directly relating to what we've been talking about. So Don, take it away.
Can you all hear me?
Yes.
Yes, I can hear you.
Yes, we can hear you.
My question is this. How do the principles of scaling laws, such as metabolic rate and city population size, impact the sustainability of biological and urban systems? And what are some of the potential strategies for addressing these challenges?
Great question, and I wish I'd had more time, because that's what I think about. I mean, yeah. So let me just try to do something very quick. In biology, I said there are these quarter power scaling laws, and metabolic rate in particular scales with this 3/4 slope, and 3/4 is less than 1. We call that sublinear. And 1 is very special. If it's scaled with the slope of 1, that would be linear. And what does linear mean? Linear means if you double the size, you need twice as much energy, for example. But if it's 3/4, very roughly speaking, it means if you double the size, you only need 75% as much energy. So we are much more efficient than our dogs and cats. They use more energy per unit mass of tissue, per gram of tissue, or per cell to stay alive than we do. But we use more energy than a horse or an elephant because of this scaling law. So that has very profound consequences, this sublinear scaling, because what it means is as you grow as an individual from a baby up to an adult, and your metabolic rate is continually changing, sort of following this 3/4 power scaling law, your supply of energy cannot keep up with the demands of adding new cells, because you're adding new cells in roughly a linear fashion. And a linear demand, which is what growing means, you're demanding more cells, outstrips the supply, which is only growing with this economy of scale of 3/4. So what happens is you stop growing. That's why you stop growing, is you can't keep up. So your growth curve, so to speak, it looks like something that we call sigmoidal. It increases very quickly, looking exponential, and then it turns over and stops. And so you spend most of your life, and most organisms do this, spend most of their lives in a sort of, roughly speaking, stable state, stable configuration. You don't, I mean, you may put a little weight here and there, but you don't grow what is technically called ontogenetically. That is, you stay pretty much the same until you die. And that underlying stability at the individual level propagates through to the entire system, and so gives rise to the long-term sustainability of life on this planet, because most things, once they reach maturity, stop growing. And so that is one of the reasons, one of the major reasons why life has been around for 2 to 3 billion years on this planet, because of this stability, and it has been driven by this sublinear economy of scale scaling of metabolic rate. Now, let's move to socioeconomic systems, to cities in particular, but it's true of the whole planet. They too, I said, satisfy sort of universal scaling laws. Cities across the globe scale in the same way, whether they're in Asia, America, or Europe. And I said they scale in the same way, meaning that they're these straight lines on logarithmic plots. But here's the big difference. The big difference is the slopes, instead of being sublinear, are superlinear, meaning the slope is bigger than 1. And that comes about because the slope of it, that dynamic, has its origins in social networks, because that's what cities are for, are to facilitate social networks. And social networks have built into them, as I emphasized earlier, positive feedback. You build on each other. And so you can easily sort of imagine that gives rise to, the bigger you are, the more you get per capita, rather than the less per capita, so to speak, if you're sublinear, which is what I talked about for organisms. So as you get bigger, you get more per capita. So, and I already said it, you get systematically higher wages, more interactions, more social interactions, more restaurants, more ideas are created the bigger the city. New York is the most exciting city in the United States, probably in the world.
I mean, that's where I am right now.
It is, because it's the biggest, it's creating, it's churning stuff all the time, more and more. And that is reflected in these scaling laws having a slope bigger than 1, and it's bigger than 1 by about 15%, by the way. So the slope is about 1.1, and that's great. So that's fantastic, and that's our success. However, if you now ask about how that feeds into growth, it means instead of finite growth, cessation of growth, the stopping of growth, which is what we do, instead of that, this superlinear scaling, this continuous feedback, positive feedback, gives rise to open-ended growth, which is what we see. So that's also good, because that's what we see. That's what the economists have done and what we believe in. You know, presidents get a bunch of shit if we're not growing all the time.
Right.
So, and that's what the theory predicts. That the theory comes out of it and it predicts that. That's great. But it has built into it mathematically something that's very bad. So the good news, we have open-ended growth. The bad news is that open-ended growth leads to something that technically we call a finite time singularity. And what that means in English is that in some finite time in the future, could be next year, 5 years, 10 years, 50 years, whatever it is you're looking at, whatever socioeconomic metric you're looking at becomes infinite, which is crazy. can't have an infinite number of AIDS cases. You can't have an infinite GDP, and so on. So you reach infinity in a finite time, which is crazy. But the theory tells you what happens. It says, no, you're not going to meet, you're going to hit this singularity, and then you're going to collapse. So that's terrible. So how do you avoid the collapse? Well, you avoid the collapse by realizing that the way out of it is that you have to innovate. So that's the origin of innovation, that you innovate, because if you make a major innovation, you can start over again. So what are the kinds of major innovations that change things? Stone. You start to use stone. That's why it's called the Stone Age. Or you discover iron. That's why it's the Iron Age. It completely sets the paradigm and what determines so much of what's happening at that time.
Oh, yeah.
The Industrial Revolution, the discovery and exploitation of fossil fuels, of coal, and the concomitant development of capitalism.
Nuclear power.
Now, the most recent one, of course, has been computers.
Yeah.
And then now the internet.
Yeah.
And so these reset the clock, and we can start over again.
Innovation.
And that's great.
Yeah.
What we've done. Innovation is fundamental. But here's what the theory says. It says, in order to continue this open-ended growth, you must be continuously innovating. That is making a paradigm shift, reinventing yourself. But, well, many people have said this. It's part of what business thinks and what economists think. But this is a theory that has predictions, and it says, yes, you can do that and you can preserve open-ended growth, but you must do it faster and faster in a predictable fashion.
Yeah.
So something, I just make up some numbers now, something that might have taken 100 years to develop 1,000 years ago now will take 15 years to develop.
Yeah, Moore's Law, yeah.
Well, it's like that. So, the internet, how long did it take the internet to develop? Not very
10
long.
years, maybe?
10 years, 15 years.
Yeah.
So the next major one is going to happen
faster.
In 10 years. And then, so this is sort of ridiculous. You can't, so the question is, it's going back to what we discussed earlier.
That complex.
Can we keep up with that?
It's not sustainable, right?
And that's the point. That's the thing, that conceptually, that is not sustainable unless there's some other kind of major intervention which changes the way in which we do these innovations, which is to do with culture and social networks. What do we do to change ourselves in order to do that? And that's where I'm sort of at.
That's brilliant. I mean, I'm not just trying to stroke your ego. That's brilliant. So
well,
you're welcome. No, seriously. I don't want to keep you any longer, but I could keep going at this for hours. Please don't let me.
Well, all I can say is that people are interested. They should read my book.
Yes, please.
Honestly, I mean, it was written for quote. It was written for the quote intelligent layman. Actually, it was written for my mother.
Don just bought it. He said.
Oh, that's very sweet. Thank you. It was written purposely so that everything would be explained, and there would be no mathematics, which was quite a challenge, may I say.
Ooh.
The original Penguin, which published it, wanted me to say, okay, put them in the appendix or put them in something. But I realized that would frighten people. So eventually I spent a lot of time trying to put mathematics into English. I don't know. Some places I succeeded pretty well, other places probably not so well, but it is for someone that's interested in these ideas to really explore.
I think that's all.
And I am, as you asked me earlier, and I am now thinking again of writing another book. And someone asked, I just saw on my screen, what's the book? Do I have it? Wait a minute.
You want me to read the name of the book again?
I'm propping up my computer.
Oh, I'm going to read it one more time. We're going to read it one more time. All right, guys. The name of the book is Scale: The Universal Laws of Growth, Innovation, Sustainability, and the Pace of Life in Organisms, Cities, Economies, and Companies.
by saying, I want to talk about the consciousness of atoms, man. I'm sad we didn't get to that thing. That, yeah. Oh, well, if he wants to, I'll make a whole room about it and I'll lace him up completely, but there's no way I can do it in 1 minute. There's just there's so much. Yeah, anytime if he wants to make a room, I'll make a separate room about that and go all the way through it, man. But this is so easily doable. I mean, we've been doing it for millions of years before our vampire overlords invented themselves. So
Yeah, but let's not ignore Tree though. He did make a point. Do you have anything to reply? Okay. Okay. No, no, no. I understand some things are too difficult to get into within 30 seconds. I get it. Okay. Real quick, Tree, Don, do you have anything to say about any of that?
All I want to say is that one of the major obstacles that we're facing are systemic ones, and I think this is something that Dr. Geoffrey was talking about. Is the way the system is designed, the way the system is organized, that allows this type of exponential, unmediated type of growth that is unsustainable, also exists politically. That we have
Yeah.
to reinvent ourselves socially and culturally, and I think um, that is a very important point that he brought up, and something that I think progressive voices in general try to fight for. We might disagree on how, but I think we all agree that things need to change, to maintain.
Mm-hmm. Yeah, innovation, how he said in terms of that. Let's go to Nivik was trying to get in earlier. Nivik, did you have something you wanted to add? I'm going to go around the room, and then we're going to probably move to Discord here in just a minute.
No, not at the moment.
Okay, buddy. GHC, did you want to hop in here real quick before I start wrapping it up?
Yeah, I don't know. I think
Did we lose you? Yeah, I can hear you now.
Yeah, I think education is one of the things that is being reformed right in front of our eyes without people really noticing it. Like these Discord servers are a good example of that. I was in one 5 years ago where most people were not in any shape or form related to academia. There were some high school dropouts even there, and people just started gathering and making things. Very very different kinds of projects, and that in that case they were all trying to build educational projects like how to teach high level physics to each other without a university degree, and it was working. I mean, I'm not a physicist, but you could tell with the passage of time that people were starting to understand each other. There was one PhD mathematician and one PhD physicist that were involved in that as well, and they had like these weekly meetings where everyone would just read through a book, like a hard book, and figure things out. And I think there's no reason why that can't happen with many other engineering things, and there's good examples.
So it just becomes an engineering problem then, right?
Yeah, I'm saying engineering because we were talking about politics and everything, and I mean,
Yeah.
in innovation especially, right? Like food, in terms of food, I think politics will lead you to money, right? Will make you make statements about money, right? Free food for everyone. I think that's a bit nonsensical. I think the problem is much more, how do you teach people to make food, right? or how do you solve the food problem? If right now we're stuck in this pattern of being consumers, right? And the trick would be to figure out how to be better producers, and necessarily how to make food free, but easy to get across the world.
Well, maybe that in some ways leads us to the correct answer. Go ahead, Nivik.
But you wouldn't have control if you do that. Why would you want to do that?
What do you mean? You wouldn't have control?
He's being facetious.
Being able to fish instead of
He's
being beholden to and being needing the security in another. Like, you wouldn't want that. You'd want control. You'd want power.
He's saying in certain not you, GHC. He's saying like in certain situations people would do this.
Yeah, I get it, and people can do it, right? People play politics. Most people are not politicians, though, right? Like most people are working everyday jobs, and now with we've seen the first McDonald's that have no people working in them. All of these things are happening, and they're happening very fast, right? And I think there's never been a better opportunity for people to boost themselves up by their bootstraps, right? But it is a problem because we are